We learned earlier about different physical quantities, of which 7 are considered fundamental according to the SI system of measurements, while the others are derived physical quantities. The 7 fundamental quantities are length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These are also referred to as base quantities. All other physical quantities can be conveniently derived from these base quantities. Thus, we have relationships between fundamental quantities and derived quantities. Therefore, when a derived quantity is expressed in terms of base quantities, the resultant expression is the product of different powers of the base quantities. For example, consider the quantity force. Force is product of mass and acceleration. Mass is a base quantity, and acceleration is the derived quantity, which is the ratio of change in velocity to time. Velocity, which is also a derived quantity, is the ratio of displacement to time. Displacement, in basic terms, is length. Thus, velocity can be expressed as the ratio of length to time. Using the same logic, we can write acceleration as length by time divided by time. Thus, the expression for a quantity force can be simplified as shown. From the expression, it is clear that the exponents of mass, length, and time in the expression for force are 1, 1, and -2 respectively. These exponents of base quantities in the expression for force are called dimensions. Thus, the dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We say the dimensions of force are 1 in mass, 1 in length, and -2 in time. For convenience, we use symbols to represent base quantities as follows. For mass, we use m. Length is denoted by L and time by T. The other 4 base quantities are represented by symbols of their SI units, namely electric current by I, thermodynamic temperature by K, amount of substance by mole, and luminous intensity by CD. The physical quantity expressed in terms of its base quantities is enclosed in square brackets to show that it is an equation among the dimensions of the quantity and not among the magnitudes. Thus we can write the expression for force as force is equal to mLT power -2 as shown. Such an expression for a physical quantity in terms of its base quantities is called its dimensional formula. An equation which equates the quantity with its dimensional formula, is called a dimensional equation. Of the 7 base quantities in the SI system, we see that only 3, namely mass, length and time, exist in the dimensional formula for force. Thus, we can say that the dimensions of all the other 4 base quantities in the expression for force are equal to 0.
फिजिक्स की वजह से अब आपका सिलेक्शन
In mechanics, most derived quantities are related to only the 3 base quantities of the 7, namely mass, length and time. Let us look at another example. Let us find the dimensional formula for pressure, which is equal to force per unit area. Area is the product of length and breadth. Length and breadth represent the base quantity, length. Thus, area can be expressed as length square, and hence its dimensional formula is L power 2. We know that the dimensional formula of force is mLT power minus 2. Now, the dimensional formula of pressure is obtained as shown. Following the same methodology, we find the dimensional formula for the volume of a body. Volume is the product of length, breadth and height. Height also represents the base quantity, length. Thus, the dimensional formula of volume is L power 3. Similarly, we can find the dimensional formula of mass density, which is the ratio of mass to volume. The dimensional formula for density is mL power minus 3. So far, we have discussed derived physical quantities, namely force, pressure, and density. These quantities have units, namely Newton, Pascal, and kilogram per meter cube, respectively. But there are certain derived physical quantities that do not have units. For example, relative density is the ratio of the density of a substance to the density of water. As it is the ratio of 2 identical quantities, it does not have any unit. Therefore, the quantity relative density does not have any dimensional formula. Another example is absolute refractive index, mu, of an optical medium, which is the ratio of the speed of light in air or a vacuum to the velocity of light in the given medium. Refractive index is just a number and is significant even though it does not have any unit, because the value of mu of a medium indicates the extent to which a ray of light bends on entering the medium at a given angle of incidence. refractive index of a given medium is constant and does not have any dimensional formula. You will learn about refractive index in detail later in the course. We also have certain physical constants, each of which has a unit as well as dimensional formula. For example, the universal gravitational constant G is a constant whose value is 6.67 into 10 power minus 11 Newton meter square per kg square and is denoted by the expression G is equal to force F into distance d square by mass m square. Thus, the dimensional formula of G is obtained as shown. We obtain the dimensional formula of G as m power minus 1 L power 3 T power minus 2. You will learn about G in detail later in the course. So far, we have discussed physical quantities, which are expressed as the product of base or other derived quantities. We also learnt that a dimensional equation is the equation among the dimensions of the quantity and not among the magnitudes. But we may encounter situations where we need to add or subtract different terms involving base quantities. It is very important to know that when we write L plus L, as shown, we mean length added to length. So, we get length. Again, it is not 2 times L as we are not adding the magnitudes of the length. Similarly, if velocity is subtracted from velocity, we get velocity. Thus, Lt power minus 1 minus Lt power minus 1 equals Lt power minus 1. The table shows the list of some of the physical quantities and their dimensional formulae. You will learn about the applications of dimensional formula later in the course.